It is in process, yes, sir.
Okay,
I think it is live stream.
It is live, yeah, it is live.
So, yeah, let Mr. come and then we can start. Yeah, we can start, Rohini.
Yes, sir. So good afternoon, everyone, to the weekly online lecture series on atmospheric dynamics and its applications to climate sciences. This series is being jointly organized by South Asian Meteorological Association, SAMA, and Savitribai Phule Pune University. Before we jump on to the lecture, which will be given by Professor D.V. Bhaskar, sir, let's have a welcome address from Mr. Sunil Kariyavasan, who is former DG's Sri Lanka Met Department and member of advisory panel, SAMA. Sir, please.
Okay, thank you very much. And good afternoon to members of SAMA family and those here from Savitribai Pune University, as well as Professor Bhaskar Rao, today's lecturer, and all our distinguished participants and panel members and all. So it's with great pleasure that I welcome you all on behalf of South Asian Meteorologists Association and Savitribai Pune University to this weekly 8th lecture on atmospheric dynamics. And today it's going to be about vertical variation in geostrophic wind, thermal wind, barotropic and baroclinic atmosphere. So, in fact, as you know, the South Asian region is affected by many more weather systems. Some of them are unique to our region. I hope the weekly online lecture series on atmospheric dynamics is to enhance our understanding of the fundamental forces and processes that govern atmospheric motion, which are crucial for accurate weather prediction, climate analysis, and meteorological research as well. As meteorologists, we are constantly challenged by the dynamic nature of the atmosphere, from large-scale circulation patterns to small-scale turbulence. Every component plays a vital role in shaping weather and climate. Today's session will provide valuable insight into key topics such as vertical variation in geostrophic wind, thermal wind, barotropic and baroclinic atmosphere. And in fact, those things are much more relevant for the regions away from the tropics. Nevertheless, understanding the atmosphere is very much important to those involved in the field of meteorology. Even in other regions, due to the fact that there are various kinds of connections and teleconnections between the climate patterns of tropical and extratropical regions. Today, we are fortunate to have Professor Bhaskar Rao with us to deliver the 8th lecture of the series on atmospheric dynamics and its application on climate sciences. Professor Rao was involved in numerous ways to distribute his knowledge and experience in meteorology, and he retired from his service from the Andhra University, which will complete its 100 years long journey in the year 2026, which is in the next year. And the Department of Meteorology in the university, Andhra University, has already passed its 75 years milestone. Certainly, Professor Rao will guide us through this concept of vertical variation in geostrophic wind, thermal wind, barotropic and baroclinic atmosphere, offering both theoretical knowledge and practical applications. His expertise will help bridge the gap between theoretical meteorology and operational forecasting, equipping us with tools to improve our analysis and predictions for the betterment of the society. I encourage you all to actively participate, ask questions, and engage in discussions. The more we interact, the more we gain from this experience. Let's make the most of this opportunity to expand our knowledge and refine our skills. Once again, welcome to this enriching session. We look forward to a productive and insightful learning experience with all of you. Thank you and good luck.
Thank you, sir. And thank you also for the short introduction from Bhaskar Rao, sir. So we all and the participants are also very well aware about Bhaskar Rao, sir. They have all attended his previous lecture. So I request now Bhaskar Rao, sir, to please go ahead with this lecture.
Share my screen. Share. Good afternoon, everybody. I think the screen is visible now.
Yes, sir.
Yes, sir.
Also, the voice not bad.
No.
Okay.
Sir, full screen also is there. Yeah.
Thank you very much, Dr. Rohini, Professor Someshwar Das, Tyagi Ji, Karevasan, Divya Prakash, for your good introduction about this lecture and me. Thank you very much for the nice words you have said about. And this is the second lecture I am delivering. About exactly 4 weeks ago, I have delivered one lecture. But I'm doing it because not continuously, but according to the topics that are given to me. So today's topic is vertical variation in the geostrophic wind, thermal wind, barotropic and baroclinic atmospheres. So I will try my best to give the information about the thermal wind, barotropic, baroclinic atmospheres, because already I think some lectures have been given on geostrophic wind, but we have to start with that. So I start with the geostrophic wind to recapitulate. Geostrophic wind is a wind that arises because of the balance of two forces in the equations of motion. In the equations of motion, the equations of motions are acceleration equations, dou U by dou T, dou V by dou T, dou W by dou T, etc. In that, the important forces that are present are pressure gradient force, Coriolis force, gravitational force, frictional force, etc. We are all aware of all these forces. And somebody might have already introduced you about the geostrophic wind. If you neglect some of the terms, acceleration and the gravitational and the frictional forces, then you will be left with a pressure gradient force and the Coriolis force. If you take these two terms and a balance of these two forces, then you will have some particular kind of expressions for the wind. And these expressions are very familiar and very simple also. So Fu means U is the zonal component of the wind. F is the Coriolis force, is equal to minus 1 by rho dou P by dou Y. Dou P by dou Y is the pressure gradient force in the Y direction. And F is equal to 1 by rho dou P by dou X. So we have the U and V components expressed in terms of the Coriolis force, density, and the pressure gradient terms. So apparently these things are some kind of diagnostic equations. There is no prognostic term involved in this. That means you are not going to predict anything out of this. But if you know one particular term, then you will be able to calculate the other, especially if you know the pressure gradient force. Then you will be able to derive the U and V components of the wind. So if you take a pure balance between the two forces, that is the pressure gradient force and the Coriolis force terms, you will end up with some particular kind of a balance equations, which we call them geostrophic wind equations, as shown here. Well, we know very well that if there is a high pressure, if there is a low pressure horizontally, then the particles would tend to move from high pressure region to low pressure region. So in this particular case, you have a high pressure here, you have a low pressure here. The isobars are being drawn here, 512, 508, 504, 500, etc. So the pressure gradient force exists in this particular kind of a scenario from high pressure to low pressure. The pressure gradient force is being directed from the region of high pressure to low pressure. So it would be like some from here to here, from here to here. So the particles tend to move from the region of the high pressure towards the low pressure. But from the equations of motion, we know a Coriolis force acts as the particle starts moving. The Coriolis force does not exist if there is no motion of the particle. But as the particles start moving, the Coriolis force starts acting because it is an apparent force which arises because of the Earth's rotation and the equations of motion that we write using Newton's laws. All that you might have known before. So here, what happens is that the particle moves from high pressure to low pressure. The Coriolis force acts to the right of the motion of the wind. So the Coriolis force acts to the right, and because of this, it tends slightly tilted towards the eastern direction. And then the Coriolis force is perpendicular to that and perpendicular. Ultimately, it will reach a scenario where the particles would be moving parallel to the isobars, at which particular time the pressure gradient force and the Coriolis force balances each other. Exactly here, the particles would be moving not from the high pressure to low pressure, but parallel to the isobars. That is the nice part of it. So here in this particular case, the particles are moving, or the motion is parallel to the isobars, and where at which particular time the pressure gradient force is completely balanced by the Coriolis force. This is the concept of the geostrophic wind which has been taught to you previously. So this is just to say how we start with, because geostrophic wind is the starting point for the thermal wind too. Well, I don't know how to do this. Okay. If you see in the atmosphere, the observations show that the geostrophic wind, the horizontal geostrophic wind, is not constant with height. Generally, it is observed to vary with height. Whether it is increases or decreases, that's a different story. But it varies with height. Why it should vary with height and what are the implications we will see from this small figure. So this is the x direction. Similar picture can be drawn for y direction also. At least one, if you see, understand it, you can understand the other picture also. This is a z direction. That means height. So here you see this is one isobar, and then another isobar is there at the top. So here you see the slope of the isobars is different. At the lower level, the slope of the isobar is smaller than the slope of the isobar at a greater height. So at a slightly higher height, the slope is more, and then at the lower, in this diagram. So if this is the scenario, what happens? How do we understand about this? So if this is the case, then what do we expect is the geostrophic wind is proportional to the pressure gradient force, because from the two equations which I have shown you just before, we know that it is proportional to the pressure gradient force. So here at the lower levels, there is certain pressure gradient force, but since the slope is higher, at higher level, the pressure gradient force is higher. So what we expect is the geostrophic wind in terms of magnitude is lower here at the lower levels, but as we go up, the geostrophic wind is larger compared to lower levels. So here, this is a small scenario, and we see that the geostrophic wind is increasing with height, and that is being explained or shown in terms of the slope of the isobars. So the slope of the isobars at different levels now lead us to the reason that the geostrophic wind tend to vary with height, which depends on the slope of the isobars with height. And the reason for one isobar having higher slope over the other, why here there should be the height, because the P plus dP means this particular isobar means the pressure is same over all this isobar, and here the pressure is same. That's what we mean by isobar. So why there should be more of the slope at one particular place and why there should be less of the slope at a different place. So we can explain this using the hydrostatic approximation. Delta P is equal to minus 0 dz, or delta Z is equal to minus delta P by 0. This is a first equation which you should be very much familiar with. And so here I show a small picture. Here it is a colder air, and the distance between 1000 hectopascal and 500 hectopascal isobar, these two isobars, 500 hectopascal, 1000 hectopascal. It is smaller here. It is about 5,400 meters. And here on the right-hand side, you have a warmer air. That's what they say. Here it is the distance between 1000 hectopascal and 500 hectopascal isobars is larger. This is very, very simple for us to understand from this equation also. Delta Z is dependent on, because delta P being constant. So the pressure difference between the 2,000 to 500 hectopascal, here also the pressure difference between the two heights is same. So it is delta Z is clearly and solely dependent on the density. So because it's on the denominator, the higher the density, you will have a lower thickness, and smaller density, you will have a higher thickness. So this is very easy for you to understand in terms of the density. So from this now, using the hydrostatic approximation, I am trying to make you understand that the difference between the isobars in different regions are critically dependent on the density of the region. And the cooler region, we have a smaller thickness. The distance between the two isobars in the vertical direction is smaller. And in a warmer region, the distance between the two isobars is larger. If that is the case, warmer region means we know denser and warmer. Warmer means this is a less denser, lighter air, and this is warmer. And this is a colder air. Temperature is lesser. So here it is. Here it is lesser, colder air, denser air, warmer air, lighter air. So this is how we understand. And here it is density. Density is related to the temperature, as we know. The equation of state P is equal to R rho T, we know very well. So the interpretation can be made very easily. Now we see that the distance between two isobars in the vertical direction is dependent on the density mainly, and the density is dependent on the temperature between that layer. And here we see that and here this is the y direction. So now here we are trying to see the geostrophic wind, which is south to north. That means wind which is parallel to the y-axis. Parallel to the y-axis means south to north, and a positive meridional wind means south wind blowing from south towards north. In the meteorological jargon, that is the way we have to consider. And here we see that this geostrophic wind, the meridional wind, which is parallel to the y-axis, is increasing with height. And here also the same thing what I have shown you before. This is the pressure decreasing with height. There are three isobaric surfaces we are showing. So the wind is increasing with height because the slope of the isobar is larger, and the slope of the isobar is increasing. The slope of the isobar is increasing as you go up in the jet direction. So from the same explanation, I'm just trying to show another picture. So we see here that delta Z, the height between the two pressure surfaces, increases with the decrease of density, and the geostrophic wind in this particular case, meridional geostrophic wind, it increases with magnitude because the isobaric surfaces are sloping more as you go positive in the x direction. So as you go positive in the x direction from point x1 to x2, the slope of the isobar is increasing. So that's the reason why we see the variation of the geostrophic wind with height. This complements what I have said before. So here now, as we see the change of the geostrophic wind with height, I have shown you that it is connected with density of a column and also the temperature. So if we know that in the higher density regions, the distance between two pressure surfaces is going to be smaller, and in the regions of lower density, the distance between the same kind of two pressure surfaces is going to be larger. And as I said, the density is dependent on the temperature. So now we can make a statement that the temperature gradient, just like the density gradient, we have said the temperature gradient that exists along the x-axis is going to contribute for the variation of the geostrophic wind with height. So if you have agreed that I have already shown that density plays an important role, density means the temperature also. So the region where the temperature is higher, the region is less denser. Where the temperature is lower comparatively, the density is higher. And so you have a particular way, the share of the geostrophic wind now could be connected with and seen clearly that the horizontal temperature gradient. In the picture we have shown here, and here it is cold. That means temperatures are smaller, temperatures are higher here. So if there is a variation of the wind as that is being explained from this particular picture, then we can say that there is a horizontal temperature gradient at different levels that will contribute to the change in the geostrophic wind with height. So the horizontal temperature gradient is the main reason and to explain the vertical variation of the geostrophic wind. So the vertical variation means we call it vertical share of the geostrophic wind. So now we make a statement, the vertical share of the geostrophic wind is the difference. If I make a statement, that is the difference between the geostrophic wind at two levels, and this particular difference in the geostrophic wind between two levels is now called thermal wind. So I have shown you the variation of the geostrophic wind and how it is being connected with the density, how it is being connected with the temperature. And now I am just showing you why we call it a thermal wind, because this vertical variation of the geostrophic wind is rising mainly due to the horizontal temperature gradient. So the vertical share of the geostrophic wind is called thermal wind because it is the share is happening because of the temperature difference between different regions, horizontal temperature differences. So let us come to some mathematics. This mathematics should be very, very simple for many of you. But anyway, let me see, because there could be some new people coming in. To derive the expression for thermal wind, I take this expression for geostrophic wind and FV and FU. These are the two expressions for the geostrophic wind, as I have said. This equation is the hydrostatic equation. This is the equation of state. These four equations are very much familiar to you, taught in earlier lectures. So now I use them. What I am doing is between this V geostrophic wind equation and the hydrostatic equation, and from FV and use the equation for V geostrophic wind and the equation of state. Similarly, the hydrostatic equation and the equation of state. That means nothing but substituting for rho is equal to P by RT in these two equations. in these two equations, 1 by rho. 1 by rho is nothing but now RT by P. So if you substitute, what you will get is some equation like this. I did not write all the terms that come in between this. This is a very, very small, simple mathematics. So you have a P here, RT by P, you will get it here. 1 by P dP by Tx, we write it as dou by dou x of log P. And the other term is here. How you got this dou by dou x of log P is because substituting for rho here, in this case, and you will have 1 by P dou P by dou x. Combining 1 by P into dou P by dou x, you can write it as dou by dou x of log P. So similarly, we can write for Fu also, the Fu equation also, this and the combined equations from these two, we can modify and then get these two terms very easily. This is a very, very simple thing, which you can do very simple. I don't think you will miss it. So from the geostrophic wind, Fv and Fu now written in terms of or we have substituted, and the hydrostatic equation we have substituted, and because you substitute here the same thing, you will have 1 by P dou P by dou Z, so you will have dou by dou Z of log P. I don't think you will have any problem in understanding or getting these three equations from the previous equations. There is a very, very simple way. You just substitute and then you will see it very easily. So now what we do is we differentiate this equation and this equation with respect to Z, and you differentiate this respect to X, for example, in the beginning. Differentiate this equation, Fe equation with respect to Z, and the hydrostatic equation with respect to X, so that you will have two terms of the same time, and those two could be neglected. Will be cancelled. So you will get a diagnostic equation directly. So by doing so, but you can eliminate, you can combine these two equations after cross differentiation, this with respect to X and the Z and this with respect to X, then you will arrive at some simple equation, dou by dou Z of Fe by T minus dou by dou X of G by T, dou by dou Z of Fu by T is equal to dou by dou I of G by T. These are very, very simple, small algebraic calculations, which calculus things, which you will be able to do it very easily. So I assume that this is a very small modification. Now we have two expressions, one from U equation for the geostrophic and another equation for the U. Now what we do is, now we expand this derivative, dou by dou Z of Fe by T. So dou V by dou Z is equal to G by Ft dou T by dou X plus V by dt of dou T by dou Z. So this is very simple. Just expand and then you will see two terms on this particular side. So you have two terms now from only two on this side. By expanding dou by dou Z F, you take it out, dou by dou Z of 1 by T, dou by dou Z of dou V by dou Z, and Vf you take it out, and dou by dou Z of 1 by T, that is minus 1 by T squared dou T by dou Z. So that is simple differential, which all of you are familiar with. So if you do that, and you will get these two equations. This is also not very complicated. So I presume that you will arrive at these two very easily and very simply from the equations which I have shown. So dou V by dou Z is equal to G by Ft of dou T by dou X plus V by T into dou T by dou Z. Similarly, dou E by dou Z is equal to some minus G by Ft dou T by dou Y plus U by T dou T by dou Z. See here, there are two terms. This is the left-hand side is vertical variation of the V component of the wind. Here, geostrophic component of the wind. And on this side, U means it is the zonal component of the geostrophic wind. And that is the vertical variation of U geostrophic wind, vertical variation of the meridional geostrophic wind. On the right-hand side, you see one term is the horizontal temperature gradient. That is dou T by dou X is the horizontal temperature gradient. Here it is in the X direction. And in the U equation, the first equation is dou T by dou Y minus or whatever. So this equation is a horizontal variation of the temperature in the Y direction. So one is the horizontal temperature variation in the X direction, Y direction. And there are two terms, one term extra in each of these equations. This is a vertical variation of the temperature. Dou T by dou Z is the vertical variation of the temperature. And this V and U shows you the slope of the surfaces, isobaric surfaces. Y is equal to mx plus c. So if you have some U here, then that shows the slope of the isobaric surfaces. So these two equations which give us a mathematical equality, vertical variation of the V geostrophic wind, vertical variation of the U geostrophic wind, and both are expressed in terms of horizontal temperature gradients plus vertical variation of the temperature. So you have both components. We'll see what it means. For example, at this particular stage, we can see what is 1 by T dou T by dou Z. 1 by T dou T by dou Z here. 1 by T dou T by dou Z. 1 by T dou T by dou Z. So we are trying to assess the magnitudes of the terms, and especially the second term on the right-hand side. And in terms of the vertical variation of the geostrophic wind. So normally, if we see in the atmosphere, the dou T by dou Z is nothing but the lapse rate, dry adiabatic lapse rate, or some lapse rate, which is the highest value is 9.8 degrees Kelvin per kilometer. And if you take, it is only about 4% per kilometer. So the correction term, which actually implies the vertical variation of the temperature, is only of the order of 4% per kilometer. The variation, how much it contributes, is only 4% per kilometer. And if you see about the wind, normally the vertical share of the winds, westerly winds in the middle latitudes, if you see, it is 25% per kilometer. That means normally we see a share of 20 meters per second with a westerly jet wind attaining about 80 meters per second at higher levels. This is some observation which I am talking about. Everybody, maybe many of you might have heard about the middle latitude westerly jet, westerlies and the westerly jet inside that at higher levels. So we observe a westerly wind here of a magnitude of about 80 meters per second or so, and the share will be about 20 meters per second, and which means that it is about 25% per kilometer. So normally, from what we say, considering the magnitudes of the two terms, the second term is generally very, very small and could be considered or could be neglected under some situations, not all the time. We will see, you will appreciate it a little later. But for the timing in the large scale circulation things, we can say that the second term, that is the term that involves the vertical variation of the temperature with height, could be neglected. And if we neglect these correction terms, now we can straight away write dou V by dou Z is equal to G by Ft into dou D by dou X, and dou U by dou Z is equal to minus G by Ft into dou T by dou Y. So if you accept these two, how we got them, now we see what is V. What is V is the meridional geostrophic wind. That is what I said. That is the V, positive V means south to north of the wind. And positive U means west to east is positive. So south to north, west to east. How, if dou V by dou Z is to increase, dou T by dou X should increase, which is there on the right-hand side. Dou T by dou X increase means temperature is increasing in the X direction. X direction means as you move from in the towards east, from west towards east, if the temperature is increasing, dou T by dou X is positive, then we call it increasing. Dou T by dou X is increasing means T is increasing as you move from west to east or in the positive X direction. So the meridional geostrophic wind, vertical variation of the V geostrophic wind is dependent on the west to east increasing temperature, west to east increasing temperature. So this is why I'm stressing it. This is very, very important for you to see here. So the south to north wind is increasing with height if the horizontal temperature gradient is such that T is increasing positively in the x direction. Okay, this is very important for you to remember. Similarly here, the U component, the U, west to east geostrophic wind is increasing with height, and you have a minus sign here, So dou T by dou Y means T increasing in the Y direction. That means as you move from in the positive Y direction, if it is increasing, that works negatively. So oppositely, if the T is increasing towards decreasing Y, then dou T by minus of dou T by dou Y is positive. So U is increasing with height if the temperature in the Y direction, if the temperature is increasing towards the south. If the temperature, north-south gradient of the temperature is in such a way that the temperature is decreasing north to south. So now we can see the V wind is associated with the increase of temperature, the height, increase of west to east is associated with the increase of temperature to the south. This is a very important concept which you should have understood properly. So we are going to make some important deduction. So this implies that the vertical share of the wind is a kind of a vector. It's a kind of a vector, which means that it has a magnitude. What is the share of that and what is the direction of that? So the direction of the vertical share of the wind or the thermal wind, what we call it, I can start calling this as thermal wind components in the V direction as well as U and V directions. So the thermal wind now can be said that the thermal wind also has a direction which blows such a way that the lower temperatures are to the left of its motion in the northern hemisphere. Okay, it's very important. We are now talking about the northern hemisphere. So these two equations, as I have interpreted, the V wind increases if your T is increasing in the positive x direction. So south to north wind means you will have lower temperature to the left or to the west of its motion. So similarly here, the west to east wind is positive if the temperature gradient is blowing from north towards south. That means towards south it is increasing, north it is positive. So you have the west wind is positive and the lower temperatures will be to the west of its motion. So now from the equation which we have derived, the thermal wind are also, which is the vertical share of the geostrophic wind. Now we are saying that it is a vector. That means it has a magnitude. The magnitude is proportional to mostly to the temperature gradient, horizontal temperature gradient, and the direction is parallel. The direction of the thermal wind will be in such a way that the lower temperatures will exist to the left of the direction of the thermal wind. So we will be having a direction that is defined to the thermal wind, and the location of the lower and higher temperature with respect to the thermal wind are also being identified through this equation. Okay. So if you, from what we have learned so far, so the thermal wind contributes to the increase of the geostrophic wind with height if the temperatures are going to be to the left of its motion and less to the left of its motion, more onto the right side. Now I will show you an example which will make your understanding much better. The equator to pole temperature gradient, equator regions are hotter, polar regions are cooler, and so we have a normal meridional temperature gradient with warmer temperatures near equator and going down towards the pole. And how does this contribute in the large scale circulation? So here I show an example. The polar regions are cold. The southern tropical regions are warm. So this red arrow, orange arrow indicates warmer air. And this blue arrow indicates cooler air. And here we show the isobards. Here the 400, 500 hectopascal isobards are at these levels. This, if you say this Z. And on the warmer side, the same 400, 500 hectopascal lines are at a very higher Z values. These are at lower Z, this is at higher Z. Now you can make it very clear because it's a warmer region. So warmer regions, the height of the isobaric levels will be higher. And in a cooler regions, they would be at lower levels. So here on the polar region, which is colder compared to the tropical equatorial region, so you will have a front exists between these two. So you have here the pressure levels are at a very higher level, the pressures here on the colder side at lower, but how do you connect them? So there is a kind of a front that exists between these two regions. So there cannot be a sudden shift or break in the isobars. So they will be oriented with a steep gradient like this between these two. So if I select 2 points at the same Z level, here at the point A, it is about 300 hectopascal. At the point B, in terms of the geometric height, it is going to be 600 hectopascal. So here the pressure is more and here the pressure is less. So how does the particles move? How do the particles tend to move? So they tend to move from south to north. So cold air is coming from north. This air comes from the polar high near the North Pole. Warm air is coming from the south. This air comes from the subtropical high. And these two winds meet at the polar front. So this is normal. This is all climatology we know. We are trying to explain the situation. So here on the warmer side, the isobars at a very higher level. On the colder side, they are at a lower level. And the thickness gradient is very rapid between these two. And the pressure gradient between the 2 points between B and A is very, very large. And as I said, here the pressure is 600 hectopascal. Here the pressure is 300 hectopascal. The pressure gradient force starts pushing the particles towards north. So northward particle motion would tend because of the pressure gradient force. But what happens is, so anyway, directly above the polar front, the pressure gradient force, strong pressure gradient force exists. So the same thing I am trying to show in a small different perspective. So tropical region, polar region, the winds would tend to move from here to here in this direction because the pressure gradient is higher level to level. This is higher, this is a smaller pressure. So from the wind start moving from higher to lower pressures. And these winds arrows are the particle motion. And what happens is this blue or green arrow denotes how the winds get into west to east motion because of the geostrophic balance. Because as the particles move and then because of the Coriolis force, they tend to turn around, as I explained in the first slide itself, then you will see that westerly component develops because this is a cooler region, this is a warmer region, and because of the thermal gradient between these two, thermal wind is developing, which actually makes the westerly wind. Normally, the wind is westerly, small westerlies, but as it piles up as you go high, and which will lead to the formation of increase of the westerly wind with height. So the same thing, these blue lines are polar regions on the polar side, warmer side, polar front, and the middle latitude jet stream is found exactly above the polar front. So here above this, you will have the jet stream that is appearing, which is a very great example what we observe time and again in the atmosphere. It's a climatological feature, and it has to be explained, could be explained only because through the thermal wind relationship, whatever small equations I have shown and whatever the equations have indicated now clearly show, and then gives us a clue to explain the middle latitude jet stream because of the thermal gradients that exist from equator to polar regions. So try to understand that. I try to give some example, physical insight, how the thermal wind occurs and how the thermal wind makes you to make the wind strengthens. Well, coming back to some mathematics again, and we see that, let us see some other properties associated with this thermal wind. And this is nothing but what we have seen before. Dou V by dou Z, that's what we have said. The same thing is being written instead of dou T by dou Z, dou T by dou X, dou Z by dou X. We can write that. So delta V is approximately G by Ft, dou T by dou X into delta Z. We can write this very easily. Delta U is equal to, this from the thermal wind equations. We are just writing that. And delta U and delta V denote the change of the wind in the U wind and V wind with height. For example, if we take the T and dou T by dou X, T and dou T by dou Y in the layer, some mean values in the layer. So now I say that T and dou T by dou X and T and dou T by dou Y, if we take some mean values within a layer, so delta V, that means delta V or delta U, how it changes. Now we can see very clearly. This is a small picture, very small. This T plus 3 means higher temperature here. T plus 2 decreasing. So this particular area is cooler than this particular one, warm here, cooler here. Now, in this particular scenario, for example, if there is a wind at lower level, this particular wind, this solid line from this particular point, if this is the wind at a lower level, what will happen? See, follow very clearly. Because of the temperature gradient, thermal wind develops. So this particular area is the one that represents the thermal wind, and this thermal wind is parallel to the isotherms and the lower temperature to the left of its direction. Lower temperatures exist to the left of that, from the equations we have seen. So this particular one, if the lower wind is situated like this, the higher wind will be like this, because this thermal wind is to be added to the wind at the lower level. That will give us the wind at the higher level. So now you have from the horizontal temperature surfaces, if you have, then you will see a temperature, the temperature gradient leading to a thermal wind in this particular fashion that will make the geostrophic wind at the lower level to become a geostrophic wind at upper level. The dashed lines or at the upper level. Similarly here, if the geostrophic wind is at the lower level, the thermal wind is again the same. So it will, the upper wind is the dashed lines here. Contrastingly, if the wind is moving from this particular point to this particular point, still the thermal wind will be in the same direction with the temperatures, lower temperature to the left of its direction. So the thermal wind will be like this. So what happens is this lower wind would now become this dashed line wind at a higher level. So here also the lower level wind, the thermal wind and the dashed line denote the upper level geostrophic wind. So in both the cases, there is it is very easy for us to understand how the thermal wind exists because of the temperature gradient and how it would contribute to the variation of the geostrophic wind with height. So here the wind has, from this particular direction, it moved into this. That means there is a clockwise transformation of the wind. That means the direction of the wind change is clockwise from a lower level to higher level. From a lower level to higher level, the thermal wind is contributing to clockwise turning of the wind with height. So this clockwise turning of the wind, now I'm saying, but I will show you, but I will say, they call it veering. And contrastingly, here it is moving anti-clockwise. So the lower level wind is here. And because of the thermal wind, it is becoming like this dashed line. From here to here, it is becoming this. So in both the cases, what is happening is the wind is turning anti-clockwise. And this small figure will give us so many clues. So here we are saying the variation of the geostrophic wind with height can be understood from the value means the magnitude and the orientation of the isotherms. Then you will have here a veering of the wind, which means clockwise turning of the geostrophic wind with height, and backing of the wind, that means anti-clockwise change of the direction of the geostrophic wind. So normally what we can do is, if we have the magnitude of the wind at one particular level, then if you want to the geostrophic wind at a higher level, and if you know the temperature between the two levels, you can calculate and actually obtain the wind at a higher level. So that's from the pilot balloon observations, etc. When we have that, we have the wind at one and the temperature between these two. Or if you have the wind at two levels, we can understand the temperature properties between the two levels. And also, I just want to say here, another important point which you need to, I will anyway show. From this point, wind is going in this direction. From this point, wind is done. That means here in both these cases, the wind is blowing from a region of higher temperature to a region of lower temperature. So what is that? We can say that this particular kind of wind direction at a lower level, it is advecting higher temperatures. It is advecting higher temperatures onto as it is moving. And here these two indicates that the wind is moving from a region of lower pressure to lower temperature to higher temperature. So these two particular cases indicate cold air advection. These two cases indicate warm air advection because the wind direction is here, blowing from warmer to colder region, and these cases the wind is blowing from colder to warmer region. So we can also say that warm air advection leads to veering of the wind or clockwise turning of the wind with height, and cold air advection lead to anti-clockwise turning or backing of the wind with height. So what I have said, showing that picture, now you can read here. It can be interpreted that in the regions of the wind blowing from warmer to colder region, the wind will turn clockwise, and which is called veering. And alternately, the wind is blowing from colder to warmer region, the wind would turn anti-clockwise, which is called backing. So these two concepts, veering and backing of the wind, how the wind would turn with height, how it is being associated with warm air or cold air advection, is very, very important in the forecasting point of view. Later at some stage, if you remember these concepts, it will be very much helpful for you to apply these small thumbs up rule. Then you will be able to interpret and explain the observed weather patterns, or even infer the future weather patterns very easily. So the same thing I am showing for the one So the lower level geostrophic wind is in this direction. And this is warmer region, this is colder region. So this is a warmer wind going towards colder side. And the thermal wind exists in this direction because from the direction of the thermal wind, cooler air is onto the left of its motion and warmer one is. So this should be the direction of the thermal wind. When it happens, then the wind at the upper level will be this blue line. So similarly on this one, this shows if it is moving from colder, low level wind is like this. Again, the thermal wind is similar in this one because the colder temperatures onto the left of the motion, and because of this and this, the upper level geostrophic wind will be the blue line. So I have tried to put in some pictures to make you understand, appreciate how this thermal wind and the cold air advection, warm air advection, how it helps. And there is some equations, mathematics we have shown. Mathematically, we have shown how this happens. And as I said before, if you have a pilot balloon observations, wind observations at different levels, you will be able to understand the orientation of the variation of the temperature structure between the two levels, where how they are oriented, which side is higher temperature, which side is lower temperatures. Well, so far we have considered the equations on jet coordinates. That means level surfaces, geometric height, and how the pressure varies with that, because that is the standard way of doing it. But we will see on an isobaric surface. That means if you consider pressure as a vertical coordinate, then what happens is at each one, instead of the pressure on a level surface, now you will be able to see the height of the isobaric surface. On an isobaric surface, there is no variation of the pressure. So you will see what is the geometric height of the isobaric surface at that particular point. So we will try to transform the equation, which is very simple. Already they might have taught you how to transfer these equations. That's a very, very small, simple mathematics. I don't show it here, but we can write dou u by dou z. These two terms are already here. Already they are shown here, shown before. I'm just borrowing them. And the geostrophic wind equations on a P surface, I'm not making the derivative of that because somebody already might have shown you what is the geostrophic wind on a level surface, on a P surface, because I understand that going through, somebody had already talking about the isobaric surfaces, coordinate, pressure coordinate, and some of these things. So it will be too much time for me to get into the derivation of these equations on a P surface. But if anybody wants, maybe I can communicate with them individually. So V is equal to G by F into dou Z by dou X and a P. So pressure surface, you will have Z instead of the P. So you will have dou Z by dou Y P. So substituting for U and V in this equation, you will get this equation simply. You will get this very easily. That means substituting for U and V in this equation, for U here especially, then you will get this. And you see, similarly, you will, and whatever that is, I'm sorry, this is, this big parenthesis, whatever these two terms what are there, they give you dou T by dou Y on a P surface. These two terms combined, the transformation, when once you do it, this equation, this term plus this term, both of these two combined is dou T by dou Y on a P. So that particular part I'm not doing intentionally, but it can be done very, very easily. We do it time and again in the classroom. So that's not a very complex part of this. So I also presume that somebody might have shown you the transformation from the Z to P coordinates. So we can write very easily dou U by dou Z is equal to dou U by dou Z is equal to minus G by FT into dou T by dou Y in a P surface. Similarly, dou V by dou Z is equal to G by Ft on a P surface. On a P surface. That means the vertical variation of the V and U now can be written in terms of the temperature gradients on a P surface. Temperature gradients, horizontal temperature gradients on an isobaric surface. Okay. And one wonderful thing is here you don't have two terms. Previously in the Z coordinate system, when we have seen, you had two terms. I try to explain what is the magnitude of the second term, what is the magnitude of the second term, and then try to neglect that. But here, if you go into this, you don't have the second term. So these are exact equations. We are not going to neglect any terms in this particular one. So dou U by dou Z is equal to minus G by Ft dou T by dou on a P surface. Dou U by dou Z is equal to G by Ft dou by dou X on a P surface. So it is unlike the Z coordinates. We have the exact equations. The vertical variation is being given by the horizontal temperature gradients in the X and Y directions on an isobaric surface straight away. No neglecting. So the isobaric analysis is many times held. Actually, after going through some meteorology, we do everything in the isobaric coordinates only. Okay, so now coming at this another important application for this. If you use the hydrostatic equation 1 by P dou P by dou minus G by RT, this is a hydrostatic equation. This minus 0, rho is equal to P by RT. So we do it. Now integrate this equation with respect to P1 and P between two pressure levels. You will have actually dou by dou Z of log P here. And if you differentiate with respect to P, and on the other side, you will have delta Z. And between Z1 and Z2, between the two level surfaces that correspond to P1 and P2. So you can write down taking the mean temperature. That means you are not considering the temperature variation in the small layer you consider. You can write down this from this integration. You can write Z2 minus Z1 is equal to R by G into T bar, but log P1 by P2. R is constant, G is constant, temperature is mean we are taking. So Z2 minus Z1 is clearly now written in terms of the P1 and P2 and the mean of the temperature, mean temperature of the layer. So now I will say something. So here, coming back, here it is a cold array, 1002 hectopascal, 500 hectopascal. The difference between the two isobaric surfaces is same, but they show smaller thickness here. Now I started using the word thickness of the pressure surfaces. And normally we take only 1500. That means at the lower level, as you pass through, learn a little more of meteorology, you will appreciate why we take 5000 to 500. And you will see it. You yourself will understand in few minutes. So here, the thickness of the 1000 to 500 hectopascal layer is smaller. It is larger. And now you can say very clearly, because it's a colder air, it's a denser air, it's a warmer air, lighter air. So this is how the thickness, now we are talking about in thickness, this is a larger thickness. The same isobaric surfaces will have larger value of Z1 minus Z2, and here it will have a smaller value of Z1 minus Z2. So now we know that. Now here we say we talked about the density here, denser air, colder air, warmer air, lighter air. But the density is a function of not only the temperature, but also moisture. So normally we have to consider both the temperature and moisture. So the thickness will increase if the virtual temperature, I don't know, I don't want to go into the definition at this particular stage, but you might have known, otherwise we have dealt with it elaborately in the thermodynamics part. Virtual temperature is one in which which actually the moisture also is being considered. TV is equal to T into 1 plus 0.608 Q. Humidity will be there in that. So virtual temperature includes both the temperature and the moisture. So normally we prefer to put virtual temperature, and we can say that if the virtual temperature increases, then the thickness will increase, or if the virtual temperature decreases, either the temperature or the moisture content, either of which may happen, then the thickness will decrease. And the same equation I'm showing, the most common thickness charts are used are 1000 to 500 hectopascal. And this is the distance between the elevation of the 1000 and 500 levels, because this is what concerns the lowest layer of the atmosphere, and most of the weather happens in this particular layer, and how the temperature changes, density changes, everything that is indicated. So the pressure changes in the lower troposphere can be understood and interpreted by noting down or considering the thickness values, or normally we also make thickness charts, which you will appreciate later. So, here, what we can see is from this particular equation, please remember this. I think I have suggested you can actually compute the mean temperature. You can compute the mean temperature of the 1000 to 500 hectopascal layer, considering for different thicknesses. If you have a thickness value of normal 5,000, because it's a 500 hectopascal difference, the average value is about 5,500 meters. And so we can have some different thickness values, and you can calculate the temperatures, and you will appreciate and better this particular equation. So I think they will ask you to do that. I don't go more into that. If you have understood what I have said, you will be able to calculate these temperatures very easily. So here again, we come back and then say the thickness will increase due to warm air advection, because as I have shown you before, how the thickness will increase. If the warm air is coming and replacing the cold air, then thickness will increase, because colder air is being replaced by warmer air. It's very, very simple. Or it is a diabatic warming, if solar heating or some other reason, if the column of the air is getting heated, then thickness will increase. Or the thickness will decrease if there is a cold air advection. That means the wind is moving from a colder region to this particular region and consideration. Diabatic cooling, that means if there is not adiabatic, it is a diabatic cooling. There could be evaporation cooling, there could be long wave cooling, then in the night times, etc. So any of these things, the cooling, if there is a cold air advection or cooling, the thickness values will decrease. If there is a warm air advection or with this some particular kind of a heating of the layer, then the thickness values will increase. And normally we will see that the thickness values are higher in the lower latitudes because of the higher temperatures there, broadly climatologically speaking. And these thickness charts are very, very useful to identify fronts and boundaries between the air masses. In India, tropical regions, this may not be a very common feature, but in middle latitudes is a very, very wonderful tool for the thickness charts, as they would help you to understand the weather pattern and also make some interpretation about the weather prediction of the weather. So air temperatures, we know that they almost fall behind the cold fronts. The contours become very close and tight very near the cold side of the front. Here is some picture. The blue lines are the colder regions, the warmer ones are going red. The front is being shown on the warmer side of this one, and these lines are being packed up very near the front. That means the gradients are too large, and that's where the front happens, because I told you, I have shown you the polar front, etc. So from the thickness charts, it is possible to find the warm and cold fronts, tight thickness patterns, which we see on a chart, and where the thermal wind is changing. That means where the thermal, that means the cold winds and the warm, you can see the spacing between the warm region, the spacing between the colder one, and where the front is happening, the gradients are larger. And we see the tight packing of the thickness at the frontal boundaries. And the front actually shows toward the warmer side. And the regions of potential atmospheric development, that means if the weather is developing, that development can be seen and identified from the closeness of these contours, thickness contours. And we also many times there they will see 5,400 meter thickness line, and on the polar side of that, you on the front side, and if the thickness values are less than 5,400, on the polar side you will have snow, and on the tropical side you will have rain. So normally, as a rule of thumb, 5,400 meter thickness line is used to predict snow or rainfall along a front. So because the 5,400 contour line mostly follows the surface freezing temperature. 5,400 is a thickness one, but it is associated, that particular value is associated with a freezing temperature at the surface. And you can see when you compute the temperatures, you will be able to appreciate it much better. So I will just move on to the barotropic atmosphere. So some more minutes. A barotropic atmosphere in which the density of the air depends only on pressure. So we are trying to see a highly idealistic region where the density of the air is purely dependent only on pressure. So normally this means that the density lines, constant lines of density, what we call isopycnals, will be parallel to the lines of equal pressure, that is the isobars. So isobaric surfaces and isopycnal surfaces are parallel to each other. It also means isothermal surfaces are parallel. And so if the isothermal surfaces and isobaric surfaces are parallel, there is no possibility for the vertical variation of the geostrophic wind, because along an isobaric surface, you will not have any variation of the temperature. So normally no horizontal temperature gradients. So no vertical variation because of this. So there is no thermal wind if your atmosphere is barotropic in nature. The barotropic atmosphere is one in which the equal lines of density, equal lines of pressure, equal lines of temperature, all of them are nearly parallel. So here you can see that isobaric surfaces are black, and these green lines or blue lines are isopycnals. That means density lines. And here also the same thing is being shown. Pressure and temperature lines are parallel to each other. This is the condition, kind of situation you will have in a barotropic atmosphere. And mathematically showing the condition for barotropy is rho is equal to rho a function of P, T is a function of P only, then dou T by dou Y you can write here and substitute for this, minus dou T by dou Y, you will get it. So dou T by dou Z, you will get this. And combining these two, you can see dou U by dou Z is equal to. So we are trying to make the two terms dou T by dou Y, dou T by dou Z, as we did before. And these dou U by dou Z, now these two terms are equal. So these two terms cancel each other and it will be equal to 0. So there is no share. Mathematically, this is a very, very simple one. But as you see that this is one particular time, when both these horizontal temperature and vertical temperature gradient. Where vertical temperature, this is a horizontal temperature gradient, vertical temperature gradient. Both are becoming equal, these two terms. Previously, we said the vertical temperature gradient term is negligible, and that's why we are neglecting. But here now we see in a barotropic atmosphere, they both cancel each other, which also means that in a barotropic atmosphere, you cannot neglect dou T by dou Z in contrast with the dou T by dou Y or dou T by dou X. It's a very, very important thing to remember, but they will be of equal magnitude. The vertical temperature, vertical variation of the temperature, horizontal variation of the temperature, both of them are same, so that you cannot neglect them. And so in a barotropic atmosphere, situation is very, very different from a baroclinic. Otherwise, whatever that is not barotropic, you will not, you will have another scenario. So in a barotropic atmosphere, geostrophic wind will not have very high. And the vertical temperature gradient is no longer negligible because it is of equal magnitude with the horizontal temperature gradient term. And the constant level charts, isobars, tend to be parallel to the isotherms. Okay. So there's a simple one, but it has a lot of applications, implications. But as you learn meteorology more and more, dynamics more and more, then you will be able to appreciate. Otherwise, you will be thinking that there is no barotropic atmosphere. It is highly idealized. Nowhere you will be able to see. But in tropics, you will be able to see this particular kind of situation many times, barotropic atmosphere. Only in the Baroclinic, you will see middle latitudes. You will see that much more once. So this is just a passing comment because I don't show any proof at this particular time. So a baroclinic atmosphere, rho is a function of both pressure and temperature. And in a baroclinic atmosphere, geostrophic wind has vertical shear, and that is related to the horizontal temperature gradient. Okay, so the baroclinic atmosphere, the isobars are here. These are the isolines of density, blue lines, black lines are isobars, and temperature here. You can see these things are intersecting. Here also, isobars and isopycnals are intersecting. Here, the isobars and the isotherms are interacting. So here, the situation is very much different from what you have seen here in isobar. So they are parallel, no intersection at all. And the pressure gradients lead to the variations. Now there is one important application I will see, because later they have added that I should also talk about solenoidal circulation. And baroclinicity actually leads to solenoidal circulation. No, solenoidal circulation is nothing but when you have these intersections, you will call them solenoids. That means these small areas. So here also you will have small areas they call solenoid, but it is something to do with the thermally direct circulations. That means warm air rising, cold air sinking. This particular kind of thing happens time and again in the real atmosphere. And the baroclinicity of the kind which we have talked about will lead to some thermally direct atmospheric flows, which we call them solenoidal circulations. Solenoid is a mathematical word in which you will have small closed areas. And these areas here appear because of the intersection between isobars and isotherms. And these circulations, these direct atmospheric flows or solenoidal circulations may vary from different scales, right from general circulation, scale of the general circulation, to highly localized planetary boundary layer circulations. And normally, in the lower troposphere, if we consider ourselves, then we look into that. These circulations will often arise because of differential heating of the surfaces. And so from one point to another point, the heating is different. So thermal gradients will develop in the lower troposphere because of the type of the land surface, vegetation, etc. So differential surface heating, differential means varied kind of heating of the surface from point to point, which may happen because of the irregular terrain, height of the terrain itself, land-water contrast, land surface contrast. That means over the land, there could be different kind of vegetation differences, type of the soil which you have. All these things will lead to that. That anyway is the one. Normally, these particular ones, direct surface heating, which arises, lead to different kinds of solenoidal circulations. The two most important are widely known are one is mountain circulations, mountain valley circulations, land and sea breezes. So I will show you some example about one particular kind, land and sea breezes. So here you can see this is a land, this is a ocean. This is a land, this is a ocean. During daytime, the land becomes warmer the ocean still remains cooler in contrast. So at one time, the temperatures may be same, but during the daytime, the land gets heated very quickly, and this will become warmer. This stays cooler, so temperature gradients would develop. And what happens because of that, where the higher temperature is there, where the warmer region is there, the air tends to rise, warmer, lighter, and the air goes up. Over the warmer region, the air goes up. Over the colder region, the air comes down. So this is a low pressure. Warming means lower the pressure. This the colder means higher the pressure. So what happens is during the daytime, land is warmer, ocean is colder. This will be having a higher pressure. This will be having a lower pressure. So wind, atmosphere would start moving from colder to warmer region. So there's a higher pressure to lower pressure. Here the warmer air rages upward, goes back, and then comes down into the colder region as a downward motion. So this is a thermally direct circulation, which we know and aware about. Warmer region, the air goes up during daytime, this will go onto the ocean, comes down onto the ocean. So during the daytime, sea breeze develops. That means at the surface or near the surface, the atmosphere or the wind starts blowing from the ocean towards the land, and at a higher level above, it will be in the reverse direction. So it is a thermally direct circulation, which we see time and again. The people living on the coast experience is much better. Right now, my house is situated on the east coast of Visakhapatnam. So I very much enjoy and appreciate this phenomenon. So anyway, this sea breeze we see on late summer afternoons. And what happens is the effect of the circulation, when it develops, it will change the orientation of the density lines and the temperature lines, and it will make it parallel. That means the baroclinic state will be disturbed, and as there is a thermally direct circulation, the atmosphere tend to go to a barotropic state. That actually happens, and you see that the same sea breeze would not continue throughout the 24 hours, but at some time there would not be any movement of the air at the surface, and the pattern would switch back. So there will be land to sea in the night, and then during the daytime, when it is warmer, it would be from sea to land near the surface. So this is what probably what all I wanted to say about. And as I said, the thermal wind equations could be derived for the geopotential, density, as well as virtual temperature. And so I think I have given enough information about the topics which have been allotted to me. I stop here, but I can share. I actually made a derivation for the thermal wind for the virtual temperature also. I will share the PowerPoint with the organizers. I think they can pass it on to the participants. I have no objection from my side, but you can also do some exercises and then try to make the thermal wind equations for geopotential, moisture density, virtual temperature, anything you like. Thank you very much. That's what all I would like to say about on the topic that has been given to me, and I would be very happy to clarify any points as to the best of my knowledge. Thank you.
Thank you, sir. Very elaborate and with examples. So very nice, sir. Thank you. Before we go on to the question answer session, we would like to take photo quickly. So I request everyone to please switch on their cams.
Maybe Professor Bhaskar can unshare the screen.
Unshare.
Yeah.
Okay. How to unshare? Okay. You're sharing screen.
Tyagi sir, Dr. Mohan.
I don't know how to get this.
Sir, if you go to, there will be stop sharing will be there on the top panel. Red button, stop sharing.
Okay, got it. Stop sharing. Right.
Yeah.
Right. Thank you.
Dr. Mohan, yeah, the advisory panel member. Oh,
He's
Mohan,
sharing.
Dr. Mohan is with mask.
What about Mr. Karyavasam? Can you hear us, Mr. Karyavasam? You can switch on your camera, please.
So Ashwin, let's take quickly some
You
pictures.
can picture big, yeah.
You can share on my WhatsApp so that I can share it. Done? Okay. So now I request Ms. Mrunal Naik from IITM to please conduct the question answer session.
Thank you, Rohini ma'am. Thank you, Bhaskar also for this wonderful lecture. There are few questions from the audience. So first question is from Aisha. She is asking, why does the upper level pressure gradient have greater slope? Why upper level pressure gradient is more than lower, like that is P plus dP?
It is because of the temperature density of the air column that exists over a area or a region. You see, if you contrastingly look between two regions where one is less denser, one is more denser, less denser is warmer, and more denser is cooler, and the way the temperature decreases with height in that will decide you the slope of the surface, the pressure, how it decreases with height.
Yes. So the next question is from Saroj. He's asking, in the tropics where Coriolis parameter is small, how does thermal wind equation behave, and what are the implications for atmospheric circulations?
You see, thermal geostrophic wind approximation itself, as because his question is Coriolis force. So we are not talking about thermal wind, but we have to talk about geostrophic wind, in which the pressure gradient force is balanced purely by the Coriolis force. So that is the concept we learned. And very near the equator, Coriolis force is very, very negligible. So normally we expect the geostrophic wind to be applicable to make any calculation also at a reasonably higher latitude. Before that, the Coriolis force will not have enough magnitude to compensate for that. So it is not there. Geostrophic wind is not there all the time at all situations. That is one particular estimate which can give us a part of the wind that is available. That means even if the wind is geostrophic, that means it's not purely balanced by that. Now we can mathematically understand what is the magnitude of the geostrophic component and what is the remaining component. From that, we will be able to understand the situation of the atmosphere by comparing those two terms. So it is true that Coriolis force does not balance the one, but assuming that it is balanced, then normally if it is, what is the geostrophy associated, that will help us understand the situation better. Still, geostrophic calculation is helpful.
Yes, similarly, again, the question is from Sabinidu. Can the effect of Coriolis force be higher than pressure gradient force in forming geostrophic wind in any case?
No, because pressure gradient force is a natural force which acts on the particle because of the differences in the pressure. That means the density of the atmosphere differences, etc. Unless the particle is in motion, Coriolis force will not act. The Coriolis force starts acting till it gets into a balance with the pressure gradient force only. And beyond that, it cannot, actually Coriolis force cannot be one. But sometimes you will have unusual situations which will be dealt with a little later. Some Coriolis force which will balance both the pressure gradient force and the centrifugal forces, etc. But that is not the scope of this lecture, because a way answer. I'm not happy to give just a out of the hat answer, but sometimes it could be more, and the balance is not just between the Coriolis force and the pressure gradient force only in the atmosphere. There are other forces which act, but for simplification, we just take two forces and we see how much it actually satisfies the existing atmospheric situation. And in some tropical cyclones, etc., the Coriolis force does not exactly balance the pressure gradient force.
Yes, sure, sir. There is another question from Gayanti. She is asking, can geopotential height be calculated using thickness with respect to different pressure levels?
I just didn't get, but can geopotential be calculated?
Can geopotential height be calculated using thickness with respect to different pressure levels?
Yeah, yes. Use the mathematical equation. That's what I said. I did not show the thermal wind. I have shown only for the temperature. And at the end, I have also derived, but for virtual temperature, because moisture comes in, instead of the TV, we can also use phi as the geopotential. So you can calculate the geopotential using the same Z1 minus Z2 equation, but it's in a different form. You have to make some mathematics out of it. Actually, you can do it. You can write down these equations in terms of the geopotential, in terms of the virtual temperature, in terms of the density of the moisture alone. It can be done. But you have to do some small manipulation, modification of the equations.
Yeah, so there are a couple of more questions. Maybe they are out of the box, but still I will take it. One is from Achut. He is asking, why is thermal wind important in forecasting upper level winds?
Upper level winds. No, one thing, I don't know what he means by upper level winds. In my lecture, I have shown how the westerly jet stream wind, which is observed, a strong core of the westerly winds at higher level, like 200 hectopascal level, how are these being maintained? They are being maintained because of the thermal wind equation. That means temperature gradient between the equator and pole. So the upper winds, how they are being maintained, because of the thermal wind has been explained all through the lecture.
Yes, so there is another question by Krishna Priya. She is asking, where can baroclinic and barotropic waves be observed in atmosphere and ocean?
Barotropic and baroclinic waves.
Yes, can be observed in atmosphere and ocean.
Yeah, you see, we observe sometimes in the atmosphere and ocean also barotropic waves are being observed, where, as I said, barotropic condition could be observed very near to the barotropic condition is being observed in the tropical regions. Baroclinicity is observed more in the middle latitudes, and we observe these waves, whatever these are having the middle latitude, westerlies, etc., and the equatorial easterly waves. Most of them, sometimes they are barotropic in nature, but they will be modified to become baroclinic.
Yeah. Yeah, the last question is by Josen. He is asking, as for Indian subcontinent is concerned, which types of winds are predominant in different seasons by MD?
What? Please repeat.
As far Indian subcontinent is concerned, which types of winds are predominant in different seasons? Which types of winds are predominant?
Which types of
Winds.
Sir, maybe he wants to ask which type of winds are predominant in different seasons, but by IMD.
Which types of winds are
Predominant.
predominant?
Yeah, in different seasons.
Yeah, that's very well known from climatology. We
Yes.
know it very well. We see that in the winter season, normally we will have the easterlies to come in, surface easterlies. And in the summer season, normally the monsoon season, we will have the southwesterlies to be there over most of the Indian subcontinent. So the climatology shows the different kinds of wind patterns we have, because over the entire Indian subcontinent, the same kind of wind do not prevail, but we will have the circulation patterns would be to be different between the winter season, pre-monsoon, monsoon, post-monsoon seasons. That's very well known. Any climatology would give us.
Yeah, thank
I
you,
don't know
sir.
whether it helped him to understand, but the basic wind pattern is very much known.
Yeah, thank you, sir. So I guess all questions answer section is over. So yeah, over to you, Rohini ma'am.
Thank you, Mrunal. Most of the participants have also said that this lecture was wonderful and it was very, very informative. So participants from different countries have mentioned this. So I would like to mention.
Thank you very much. If because we have to come down to the student level, that's what I try to do it always. If the students are happy with what I have said, if they have understood, I would be very, very happy. And I'm very much thankful to SAMA for giving me this opportunity to share some of the information with the young students. Thank you very much. I appreciate it.
So before going to the vote of thanks, I would like to give the statistics. So 226 participants have attended this lecture, out of which around 190 participants have rated it as excellent and very good. So it was really wonderful, sir. Very informative. Now I request Mr. Ashwin Zadav from
how many?
Yes, sir.
Countries? How
100,
many countries?
220.
The participants are from how many
countries? I
countries?
would take some time to. This was a quick one I did. Maybe next time I will include countries also. So let's see. So I request Mr. Ashwin Zadav from Pune University to please give the vote of thanks.
Thank you so much, madam. On behalf of organizing committee, I extend my sincere thanks to everyone who contributed to the success of the 8th lecture in our weekly online lecture series on atmospheric dynamics and its applications to climate sciences. So we are especially grateful to Dr. D.V. Bhaskar Rao for his warm, my heartfelt thanks goes to our distinguished speaker, Dr. D.V. Bhaskar Rao, Andhra University, for delivering an enlightening lecture on natural coordinate system, cyclonic and anticyclonic gradient flow.
Is also different. The topic is different from what I have said.
Oh.
This is geostrophic, thermal wind, baroclinic, barotropic, etc.
Yeah, Ashwin, you have mixed up the things.
Oh, yeah. No, sorry.
Don't worry, I appreciate what you have said. It happens.
Actually, I made the changes, but I showed some different slides.
The welcome address has been given by Mr. Sunil Karyavasam from Sri Lanka, the former DG of Sri Lanka Met Department. So thank you very much, Mr. Karyavasam, for delivering a welcome address.
You can correct it for when Karyavasam is still looking at, maybe you can.
Right. Yeah, go ahead.
Just a minute, I will share the corrected one.
Is all one you have picked up. I think you better not read it. You have written Dr. Madalla Shrestha, but he is not here and he was there in the 4th or 5th lecture. Okay.
So maybe I would like to deliver the vote of thanks.
Yeah.
So I am really thankful for the welcome address to Mr. Sunil Karyavasan, who is the former DG from Sri Lanka Met Department and also a member of advisory panel SAMA. So thank you, sir. The welcome address was really informative. Next, I would definitely very heartfelt thanks to our own, I should say, Professor D.V. Bhaskar Rao, sir, for the lecture on vertical variation in geostrophic wind, thermal wind, barotropic and baroclinic atmosphere. And thank you to Mrunal as well as Ashwin for taking efforts to organize everything with me. So thank you very much, everyone.
So I gave actually the questions as suggested. I think
Yes,
you will do whatever that.
yes.
If you think that my PPT would help, I will send it to you, the final PPT, which can be shared with participants.
Yes, sir, please. Yes.
Thank you very much. I appreciate it.
So the participants who have registered are from 21 countries.
Okay, right.
Very quick.
Okay,
Yeah,
thank
we
you.
try. I was trying to do that.